Next speaker this afternoon is Ken Baker, who will speak on Morse-Novikov numbers of three manifolds.
All right, well, thank you very much for the opportunity to share some of my recent works with a completely different audience. So, hope this will be trigger some ideas for some of y'all and maybe get things going in a different direction. First, I should acknowledge my collaborator, Fabiola Manjarrez-Gutierrez from UNAM. So much of this work that I talk about is joint for one way or another. All right, so I thought I'd start by just putting it in a very kind of broad context. So I'm going to have a manifold, and I guess I really want it to be smooth in manifold, compact. Probably you can get by without it being oriented, but let's just say it is. You can have boundary. Let's think to be nice enough to have the rest of it work out. And if we look at a circle valued Morse function on that, that plays nicely with boundary, however you want to call that. I'll say that's regular. Well, then I can just like count up the number of critical points. It's a very natural thing to do with a Morse function. Circle valued Morse function, well, it's circles locally the real line, so locally it's just like your regular usual Morse functions. But when we're looking at a circle valued Morse functions, well, those represent maps to the circle. So we have these particular representatives of the homotopy class of maps to the circle. And well, this collection of homotopy classes of maps to the circle corresponds to the first cohomology of your manifold, right? So what we can do is we can just define the Morse-Novikov number of, say, a given Morse representative of these homotopy classes, and just say, well, the Morse-Novikov number of that map is going to be the number of critical points. And then we can just, for its homotopy class, we'll just minimize over all of these Morse functions, or circle valued Morse functions. And so that will give us a count for the homotopy class of maps to the circle that you're looking at. And well, then we just say, well, in fact, that's just first cohomology. So we end up with this kind of function from the first cohomology of your N manifold to the natural numbers. It's counting critical points and stuff. It's giving you some sort of complexity on your cohomology count. Calling it Morse-Novikov number, that's kind of borrowing or extending.
Zero?
I do want to include zero because that would be like a null homotopic map to the circle. So I don't have to. Yeah, so the zero class, you could think of a contractual map of your manifold to the circle.
So there's N, so there's capital N.
Oh, capital N. Yes. Well, good question. I'm going to let N0 be a natural. Yeah. So anyway, well, let's see. I mean, really, might as well mention Leschetz here. So by doing a point-array Leschetz duality, we can actually kind of view these classes, cohomology classes, in terms of, I guess, N-1 relative homology classes. And you can, in this codimension one situation, we can actually go ahead and represent them by preimages of regular values. So we actually have, maybe it's just more of a matter of preference here, that we can look at our circle valued Morse functions and just say, well, I can look at kind of take this as being parameterized by like the homology classes of preimages of regular values. All right. And when I look at that, I can even just kind of slice open my manifold along that that preimage, and then I have something that's effectively just a regular Morse function of a coordism from that N-1 manifold back up to itself again. Okay. So then I can just count those. That's more of a more traditional style of Morse function. And I can just count those critical points, but being myself a low-dimensional topologist, I prefer to kind of even think of these as kind of game where you kind of change your critical points to handles more of what Morse was doing. And so I just think of like, well, instead of counting critical points, let me just count handles. It's the same thing. So now I have what I'd like to call the handle number for and so all of these homology classes then give us, we have some count of the number of handles used.
Still have some problem. Know what the definition of Morse function is on a closed manifold. You have manifold boundary. I've never thought about it.
Yeah.
Make it a little more precise. Like, what do you assume of the structure here of the boundary?
Okay, so the question here was, well, wait a second, you've got boundary here. We don't normally deal with boundary. So what I did is I just kind of like shoved all that under the rug and said, well, whatever you want to make it work. That's why I said boundary is nice, and I have this word called regular to make it be whatever you need to do to make it work. So here, I know what we're going to do is we're going to just move to like dimension 3 in a second, and then we'll be more explicit about how this work. But you can see even here, like this kind of boundary, if it's some sort of cordism, I have the boundary like top up, I have some boundary that things are going out, some things that are going in. You can kind of view it as a cordism. So you have a nice direction for that. You just maybe you want your boundary divided into two components. One's the negative boundary and one's the top boundary. And you can play nicely with that, make sure that those are.
And that's going to all come out. Okay.
Yeah, it will come out. I mean, it's a totally fair question. Yeah. So I want to put it in this broad context because, well, maybe there's. I mean, it's a perfectly reasonable question to ask, and of course, you could just go ahead and do this in the closed case if you wanted. Yeah. So, yeah, really, I think the thing is, I don't understand this function at all. I understand it a little bit in the case n equals 3, but actually, to be fair, maybe in the case n equals 1 and n equals 2, I can understand it. Maybe you can't. Those are good exercises. But I think just the broad general question, what is the nature of this handle number function, or if you prefer, the Morse-Novikov number function? So I'm just going to leave it there. And today we're going to focus on what I can say in dimension 3. If you remember, I'll come out 3 manifolds. Okay. So let's just kind of take a little step back, get our heads on 3 manifolds. Of course, I'm drawing flat pictures instead of lobby pictures. But the idea here, and where I really kind of come into this, is that when you're looking at a Morse function, okay, this is more or less equivalent to what's low-dimensional topologists like to call a generalized Heegaard split. Okay. So I have a picture here on the bottom left. I have this function from a 3 manifold to the real line and some Morse function. And so as before, I see like the boundary M, boundary minus, going up to boundary plus. But then, I have actually on the far side, I have this like annulus that I've kind of noted. And that's okay, because it's just a product. So I can imagine my flow of my function of the gradient of f, it's just flowing up nicely across that annulus. So no problem, everything's nice there. And so I can talk about manifolds like that. In fact, this kind of cobordism between boundary minus and boundary plus, where those boundaries may have boundaries. Right, that's actually something we might call a sutured manifold. These sutured manifolds, you look at the Morse functions on them, they have some Morse critical points inside, 0, 1, 2, and 3. You can kind of put in little dividers, 0 and 1's lumped together, then, I've got some 2s and 3s. I'll make a little, wiggly line for that, call it S. And back up after my 2s and 3s, I maybe encounter some 1s and 0s again. I'll throw that into the F surface, then back up to S, and then maybe out my boundary. I've color coded the places that are with just 0s and 1s as red, and those with just 2s and 3s as green. Okay, so that's just kind of chopping up my manifold into kind of like these nice pieces. And why do I do that? Well, those nice pieces, if I'm starting from some surface, I attach some, flow up a little bit. I have my surface cross interval. Maybe I have some 0 handles that have appeared. Those are just balls. And then I'm going to attach some with my index point critical points. I'm just going to attach some 1 handles to that. So that gives me something that we call a compression body. It's basically handle bodies are kind of the more basic familiar version of a compression body, but these are just kind of natural little objects that we kind of have I give it more of a straight line boundary that on one side, and then we have the wiggly line boundary where you can actually find these disks that will compress, like the co-cores of the one hand. You can kind of compress these back down to just your product or those balls. And you have kind of the dual thing with the 2 and 3 handles to the degree. Okay, so what we're doing is we're using this Morse function to kind of just get this kind of alternating stack of red and green compression bodies. Okay. And what this does is this gives us something we call a generalized Heegaard splitting. I'm just going to kind of package all of the F surfaces together as F, and all the S's together as, we'll just S, just a single F. And so that splitting together, decomposing my manifold into this kind of collection of compression bodies that are meant to fit together in the way it's indicated, that's going to be a particular generalized splitting, and that that records some sort of number of handles needed. Each compression body, it's easy to look within a compression body and see, well, if I have some of this surface that I'm starting from, I don't need any 0 handles, or if I have a handle body, I don't need 1 0 handle. But then the rest, I just count my 1 handle, and I guess dualing my 2 handles. So it's really easy for the compression bodies to just count what the complexity, what the handle number is for the compression bodies. So what we're left with then is now when I stack them up, I want to be able to understand, well, maybe there's some kind of funny business between rearranging the stacking and pushing things forward. And well, this puts us in the realm of Heegaard splittings and all the theory that's already been developed for Heegaard splittings in the past, that we can start using that technology to start to understand the handle. Let's see, probably getting ahead of myself. The other thing I wanted to mention is one, thinking about Morse functions, I think of these as very kind of loose, slippery objects. I don't know, it's a little bit more of a fine thing. Maybe it's my own personal perspective. But with the handles, you kind of belonging together all of these Morse functions that kind of represent the same kind of handle structure. So it gives you a little more of a coarse object to work with. And then allows you, and at least the way I like to see it, is that it allows you to do broader moves and do bigger rearrangements that you don't have to kind of look so carefully at what's actually happening with these circle valued Morse functions, these other Morse functions. You can really just do these greater operations and changes. That's just fully carried by like this theory of Heegaard's compression bodies. And that's actually been a very fruitful perspective. We'll see some consequences of that. Let's see, what did I do next here? Yeah, so just to kind of tie it back to the more traditional, ordinary, usual version of the Heegaard splitting, we have a handle, just a single S, our F in this case is empty. And here I showed like we have a handle body below and then maybe a compression body at top. For closed 3 manifolds, it's 2 handle bodies put together. The Heegaard genus is effectively mod counting your zeros and things. Your Heegaard genus of a 3 manifold is effectively telling you your handle number. You just need to know a little bit about the boundary. Not boundary data. And then when we go to a circular Morse function, well, I have to read just stating all of this here again. You can kind of see this wrapped around, and your critical points, you kind of flow them all the way around. And in fact, once you're in this kind of circular version, you just definitely don't need any 0 or 3 handles at all. You can always find ways of canceling them by kind of going back into the canceling. So you can always cancel 0 handles with 1 handles, and always cancel 3 handles with 2 handles when you've got a legit circular body Morse function. So then it comes really nicely into these compression bodies where you can just count them, get good counts on them just straight away. So, this is another one showing more the idea of. So, what we can also do then is just go ahead and think about like our function f, our surface f, as representing, and that being the union of all of those pieces, as that representing a homology class. And then we can go ahead and think of the handle number being kind of the count over all of the circular Heegaard splittings where that collection represents the particular homology class. And this is basically the same slide again, just looking back at it, but now specialized to dimension 2. And here I'm showing a little bit more of what I mean by the boundary issues. So to a large extent, when I'm thinking of the boundary of your manifold being a link or being a collection of tori, you either want your function to kind of be, well, you can see the level sets, either kind of going around it like pages of a book, or just kind of limiting to it as if it was kind of the top boundary or the bottom boundary. So things like that, we will say that the function is regular. There's simple homological conditions on F, on Z, to say whether or not it's actually represented by a regular Morse function. So this is a very, in the end, a very mild condition to ask for, and one that's just in general satisfying. And the easiest way to make sure it's always satisfied is to just say, the entire boundary is going to be boundary plus. So we're just done, and I don't need to worry about that. Okay. So anyway, so this is the context of where we are. We have this handle number function, counting number of handles, counting number of critical points, how many you want to make for a given homology class. So what this does is then we actually, together with Fabiola, we actually investigated kind of the various properties that this has on, as you pass through the different homology classes. And some of this may be, one of those things that after you see it, it seems almost obvious. But this handle number function, it satisfies kind of 3 principal properties. First of all, it's bounded. So given a, for your particular manifold, there with its given kind of boundary structure, there's an absolute bound on the handle number. So it doesn't kind of march off to infinity at all. We can also see that it's going to be constant on rate. So if I know the handle number of a class, any positive integral multiple of that class is going to have the same handle number. You can basically just see that by just taking parallel copies of your surface. And well, between these products, you're doing nothing. There's no critical points there. So at least one side of like getting, one inequality of getting that equivalence for being constant on rays is just immediately obvious. And then it just comes a little bit back about like how do you represent multiples of homology classes? And saying that, oh, in fact, we can see it's got to be represented by, we can always represent it by a given surface and number of parallel copies. And then after that, you can actually see it's like locally maximal. So if I think of, take my homology class, and I can think now about these rays. If I kind of think about any other homology class and add on a large multiple of this, that's going to get me into the area of looking at a ray that's very close to the ray I was looking at. And kind of blending the ideas from the previous 2 allows us to then say, in fact, I know that this large multiple, that this class that I'm looking at, Z, is going to be at bigger than than those around it. It's going to be locally maximum. Maybe it's the same. It's going to be locally maximum. And once we have those 3 properties, that's actually enough to kind of fill in the gaps, extend to the rational coefficients, and then fill in and extend to real coefficients. So what this allows us is to say now, in fact, gives us a handle number function that's defined on the relative second homology with real coefficients. Now this might be somewhere where people preferring to look at, say, forms would say, well, it's more natural to look at real coefficients, looking at Morse functions anyway. And I think you could easily get at the same kind of results from that point of view. One feature, and this isn't really part of the theorem, it's just kind of straight from the definition, I think 5, is that if your class is a fiber of a fibration of your 3 manifold, then just immediately means that the handle number is 0. It's a fibration. You have a circle value Morse function with no critical points. So that's another nice bit there. So this was a slight illustration here about the tunnel number, this upper bound. So this upper bound that we got, and in fact, what motivated this investigation was when Pageantov, who introduced me to this idea of Morse-Novikov numbers, had Pageantov had asked Fabiola if there was more geometric proof of an inequality he had proven about that Morse-Novikov number was bounded above by this kind of Heegaard genus kind of count, this tunnel number of a knot. And that led us to this fuller investigation. And here's just kind of an illustration of it, in a sense, kind of how these things go. Going, this top bound is really, in a sense, taking this kind of the wiggly circle that I have in there, it's kind of null homologous. And so you can think that by adding that in, you're not really changing your class at all. And so you can kind of use that to smooth out and spread and get the however many critical points from your kind of the tunnel number from the Heegaard splitting to actually kind of count for this kind of fibration that's maybe wrapping around. And the other side is kind of a bit more easily of just taking a couple copies of your surface and tubing until you can get going from a non-zero class to getting some sort of bound on the class. But that bound is kind of based off of the Euler characteristic or genus of the surface that's representing the class. And maybe we'll say a little bit more about it, about this Morse-Novikov genus, where you wonder about the minimal genus of a surface that would be the level surface of a function that realizes your handle. Okay. Well, so what I really wanted to get into is saying, well, so we have this Handel number function. We want to have some sort of understanding of what's going on with the Handel number. We have this kind of foundation. And so what you'd like to do is try to relate it to other kind of known objects and use that at least as a point of as a counterpoint. So we can look at relationship to things like the Floer homologies, the Heegaard Floer and Simon Floer, sutured Floer. Maybe very naturally, when you're thinking about vibrations, thinking about what happens with first and norm, and then other natural operations on three manifolds, and especially non-linking exteriors, which would be doing satellite operations. So we'll next go ahead and look at these three options. So to start off with, if we're kind of thinking about the Floer homologies, when you're looking at a fibered class, your Floer homologies tend to all, in one way or another, tell you that you've got fibered class by saying, well, the kind of the top dimensional rank of your homology is 1, and and just by definition with Handel number, you've got Handel number 0. Okay, so that's an immediate thing. So you can start to say, well, what's like next to fibered? So a year or two ago, I guess, maybe recently, Baldwin and Civic looked at this idea that they called nearly fibered. So they defined a knot or a link to be nearly fibered if the top rank was 2, just 1 more. And they investigated what those kinds of, what properties those knots and links had. And together, this was extended a little bit by UPA. They see that, well, these knots and links that had their top rank equal to 2, these nearly fibered links, they had unique minimal genus cyclic surfaces, which fibered knots all do. And then if you kind of start chopping down the complement of this unique minimal genus cyclic surface and kind of squishing out, down all the product parts you can, getting rid of all the things that would be fibered, you're going to get something that's not fibered, right? So that's going to be what we tend to call like the guts. So kind of getting down at how much of the complement of this level surface is not fibered. How can you kind of squeeze those through? And you get down just doing these like product sutured manifold decompositions, you get what's called the guts. And they determined that for these nearly fiber knots and links, your guts necessarily had one of three flavors. You were either a solid torus with where you had these kind of like annuli, these kind of vertical annuli that would be wrapping around 4 times, or you had your guts ended up being like the exterior of the trefoil with a particular kind of pattern for these kind of annular structures. Well, building on this, I mean, you might want to say, well, what's the next handle number we can reasonably have for a, what's the next kind of handle number you can reasonably have for a knot? And the handle numbers with things like knots are always going to be even. So you might wonder what happens when the handle numbers 2. And what we saw is that these guys, these nearly fibered knots, don't all have a handle number 2. And we were able, together with Fabiola, we were able to show that the handle number is 2 exactly when the guts were of the first 2 types, but the handle number could be 4 when you're going to have guts of the third type. But even more so, which was interesting, is that in the very first type of guts, it was possible that for there to be alternative incompressible cyclic surfaces. So you could have another incompressible cyclic surface of non-minimal genus. Fibered knots have a unique incompressible cyclic surface. So this idea was something that was in some sense surprising, and showed us that we have there's extra kind of structure going on in these nearly fibered knots. I think one view on that is that these floor homologies only tend to be looking at tend to only see norm minimizing things. So once you're looking at something that's not minimal genus, they maybe tend to not see that. We were able to actually also get the first example of one of these nearly fibered knots with an incompressible cyclic surface of high genus. So it ended up being a 16 crossing knot. They had actually gone through and looked at the tabulation of up to 15 crossing knots and found the nearly fibered knots. So, and 16 is just after, well, maybe these days now it's 16, but just after the tabulation. So we were able to find this just kind of by hand. 16 crossing knot that was nearly fibered and yet had this extra incompressible cycle. And able to come up with like explicit pictures of it.
How many 16 crossing knots are there?
More than I can count my fingers. But over, and maybe you just want prime ones. Yeah, I think over 100,000. There's lots. I might be out in order of magnitude. All right. So next up, thinking about the minimal genus, we bring up this idea of person. And I think this is maybe the more attractive spot to look, especially given the nature of the structure we've seen of this handle number function. So I'm normally with other low-dimensional topologists, I probably wouldn't say much about the Pearson norm. But this is a function from the second homology, the non-zero classes, where you're going to count the negative Euler characteristic of representatives of your second homology class, but you're going to throw away any spheres and disks. You're going to throw away the spots that the guys that would have positive Euler characteristics. And those surfaces you tend to want to get rid of regardless anyway. So you're getting this kind of well, it's actually a pseudo norm instead of an honest norm. But Thurston showed that aside from being a pseudo norm, where maybe you have your class realized by annuli and tori, aside from that, you actually have a nice this function x is actually a norm that extends over to real coefficients as well. And then, in fact, it's got tons of nice properties that kind of record a lot of the structure of what's going on with these second homology classes. So you have something called a unit norm ball. If you have a norm, you have that. As long as it's actually a norm, not just a pseudo norm, it's legit ball. Otherwise, you might have vertices at infinity. But this is some sort of, it has the structure of a polyhedron. And if you have a fiber class, it's in the cone over a top dimensional face of this ball. And every other class in the cone over that top dimensional face is also fiber. Right? And so it gives a nice kind of parameterization, a way of kind of looking at all of the fiber classes together. So maybe you have many different fiber faces, these different top dimensional faces that are recording the fiber classes. But it gives this kind of nice structure. And then if I'm going to be thinking about handle number, well, I already know on those fiber faces, that's where my handle number is going to be 0. Moreover, this Thurston norm ball, this ball is giving me kind of already a structure on which to decorate with the handle number, right? And we're going to look at a couple of examples, just some small examples here. Two simple examples, two simple, which are too simple, because it's just, when you're looking at the exterior or not, the second homology is just one-dimensional. So you don't really see much of this polyhedral structure. We have the 0 class, which kind of comes from like the tunnel number, where we can see what the handle number of the tunnel number is. So I have like in the middle of on both of these, I have the trefoil, see there, and then over here that 5-2 knot. For both of those are 2 bridge knots, and so we know that they have tunnel number 1. And we count up all of the handles there. We have a handle body with a 0, 2 1 handles, and then we have a single 2 handle, and that's enough to get the exterior for the 0 homology class. So that's why we have a 4 on both of those guys at 0. And then for both of these guys, they're also represented by have kind of the homology class kind of dual to the meridian going around the knot. And those they both have genus 1 cipher surfaces realizing that class. Trefoil is actually fibered with that genus 1 cipher surface of the fibration, so we can put zeros out there. Because of the nature of the manifold, it's symmetric, so boundary structure is nice, so we'll have the kind of nice symmetry there. So on one side, the other, it's just reversing the orientation. For the 5-2 knot, though, it's not fibered, and we can actually see that this surface here actually realizes the handle number 2. I don't know if this picture is terribly convincing. I'm sure it's not, but we can draw something more. We can explicitly see that it's actually. But if we start looking at 2 other links, like the Hopf link or the Whitehead link, so these are 2 component links. Their second homology has rank 2. So when we're looking at the unit ball or the boundary of the unit ball, we have we kind of parameterize things with the circle, and then we have the 0 class in the middle. Well, if we're looking at T2 cross I, well, every like curve in the torus cross I is going to give you an annulus that is a fiber. Okay, so for the Hopf link, we have like fibrations all the way around. And then, well, in fact, the Hopf link is a 2-bridge link. So thinking about both of those boundary components as being positive boundary, that's also giving me kind of the handle number 4 picture. If I were to put one boundary component down below, well, then it would just be a product that's T2 cross I, and we can count 0. So that kind of declared, we're going to just go ahead and put the boundary BL on positive. More interesting is perhaps the Whitehead link. So this one, we actually have the structure of the first form here. It makes this actual diamond. And the faces of the diamond are all fiber faces. And then we have kind of non-fibered vertices. And from looking at those non-fibered vertices, you can actually, like the surface F represents, that's shown here, represents one of the vertices of that diamond. And one can actually calculate that it has a handle number. So we can get kind of structure like this. This is telling us a little bit about the structure of the handle number function, especially as it relates to the first. So this starts one thinking in the right direction. Okay, if you want to think about the relationship of the first norm, is the handle number of a non-zero class actually realized by all of the, say, minimal genus representatives of the class, all of the top representatives? And I think that's a very natural question, because usually you think that the minimal genus guys have everything that goes nicely. But in fact, Goda, in the 1990s, he was studying handle numbers of Cypress surfaces. Look at the exterior of a Cypress surface, call that a sutured manifold, and count like it. Look at the Heegaard splittings of those things. He came up with this really neat example where it's a single knot, it's a two-bridge knot. And this two-bridge knot is obtained from like doing a plumbing of two of these genus 1 Cypress surfaces of the 5-2 knot that we were just looking at. But when you're doing a plumbing, there are more than one way to do a plumbing at the same site. And what he showed is that the two surfaces you get actually have different handle numbers. These are still genus minimizing surfaces, but one of them actually realizes the handle number, whereas the other does not. So, you know, that's actually really surprising, I think. So you want to actually say, well, maybe at least one of them, you have at least one surface is realized by a top or a norm minimizing surface. But fairly recently, this past year, Fabiola and I actually managed to concoct an example where of a knot that's genus 1, but the genus with a unique genus 1 Cypress surface. But that genus 1 Cypress surface had higher handle number than a different genus 2 Cypress surface. We did this by looking at first an annulus in the boundary of the genus 2 Heegaard splitting of the 3 sphere. And then we attached a hop band onto it to make like a whitehead double at a nice genus 1 Cypress surface. But instead of looking at the annulus in that genus 2 surface, if you kind of traded that annulus for the complementary twice punctured torus, and then continued banding that together with what was left of the hop band, that gave you a genus 2 surface with the same boundary. But then we were able to show we could actually get a lower handle number. By having this be a genus 1 knot, in fact, a whitehead double, we were actually able to then control and make sure that there were no other genus 1 cycles. And so, you know, this actually kind of really threw off the rails of, you know, hoping that there was anything very nice with in relationship to the first one. So you might wonder, say, well, first, when is it actually realized by a top? Can you say something? When do you know which classes are going to be realized by a top Cypress surface? That like Cypress surface. When is the handle number actually going to be realized by one? When is it? And one thing you might hope is then say, well, can I at least assume that the handle number, you know, because I know it's locally maximal, should it at least be constant on faces, constant on top dimensional faces? I don't know. And we're exploring that. I don't really think it's premature to report anything further. But there's a lot of structure here still left to be determined. So going even farther, we can also talk about these satellite operations. And this was actually my entry point into this theory of Morse-Novikov. Vaginov had actually given a short course here and introduced me to this problem and actually asked if the Morse-Novikov number or the handle number was additive under connected sum. And so on top of kind of getting this kind of schematic of connected sum, I have you know, kind of a little knot K2. You can see this kind of purple knot kind of tied in that little ball, and then it's kind of going to run and follow around in that K1 knot. So that would be like you can think of a connected sum as a particular kind of satellite knot, where you're going to run one thing along that through a solid torus that follows the pattern of another. And using this theory of like generalized Heegaard splittings and circular generalized Heegaard splittings, I was actually able to kind of push forward and figure out how to actually kind of groom everything correctly to actually see that in fact additivity did hold up. And one thing that kind of was a byproduct of that entire proof is that in fact you can show it came out very naturally that handle number was unchanged by cabling operations. So instead of just running a little locally knotted log with inside that purple bit there, you could say, well, let me just take some curve that runs along that boundary torus voltage and replace K1 with this kind of like a cable that's running around there a whole bunch. So, that was some interesting, behavior and gave some nice structure to what happens for the handle number, at least of knots and links. You could go forward and then further ask how does it behave under other kinds of satellite operations. Fabiola and I just looked at this flight head double. So in certain situations, it can behave very badly. You might wonder what it does. In other natural situations, you might look at maser double. That's a kind of a nice little basic one that's got winding number 1. Flight head double has this winding number 0. There's funny stuff happens at these low winding numbers. And then doing even some classic things like doing a beam double. You're trading one component for 2 components, and that thing is algebraically very kind of unlinked. So there's lots of room to kind of continue exploring and understanding what's actually going on with this here. And I guess let me just leave this with kind of a few other thoughts for further directions. I mean, I think the field's right for looking at 4 manifolds. There's been a recent resurgence in energy and techniques in 4-dimensional topology again. And I know some people are looking at it, and I probably should mention a bunch of names, but I'll skip that for making sure I skip everybody and then just a few. Then other thing you can look at are things like circular bridge numbers, where you think of let me just go and take knots and links inside a solid torus. And you can look at kind of the bridge numbers of knots and links, or think about curves inside thickened tori. You have all these different kinds of ways of looking at kind of the same way that bridge number of knots and links is analogous to Heegaard splittings or Heegaard genus. We can do the same thing with these knots and links in solid tori. And in fact, the homology theories of like annular quantum homology and all that are set up to address some of these questions as well. Similar to that, the like Heegaard homology.